Saxon's Calculus Lesson 34 is identities for the tangent function, and then area and volume. So you already know the formulas that they're giving you on page 179 in the box, that sine of a plus b is sine of a cosine of b plus cosine a sine b, all four of those. Then again, you know that tangent means sine over cosine, and that basic formula, sine squared plus cosine squared equals 1. Now they tell you to use all of those in example 1 to develop an identity for the tangent of a plus b. Now, if you remember from trig class, if you write out that tangent means sine over cosine, you're going to write out the formula for sine a plus b over the cosine of a plus b. And then even if you wrote all of those out in their long format for their equations, they don't simplify to something simple. You ended up needing to be told that whatever the first piece was in the denominator, you're going to divide everything by that, and that happened to be cosine A times cosine B. So all four of the parts end up dividing by cosine A cosine B, and when you simplified that, you got down to this: tangent A plus tangent B over 1 minus those two multiplying together. So the formula to memorize for tangent A plus B was that formula. And then it says in example 2, develop it for tangent A minus B. Well, as you would expect, you're going to do the A minus B and the cosine A minus B formulas, and you're going to manipulate, divide all four parts by that first piece in the bottom again. And so that one's going to end up giving you equals tangent A minus tangent B. See, it went from a plus to a minus. 1 minus tangent A times tangent B. Make sure that you have that as a minus. It looks like it blended in with my tangent because I was writing small there. But that's the formula for tangent A minus B. Before they move on to example 3, sorry, I didn't think that felt right. That should be a plus. 1 plus tangent A, tangent B. Both of the signs should change. This one should go from a positive to a negative, and that should go to a negative to a positive. Okay, I feel much better. Now, before they move on, they do this. And this is a calculus thing, and that's why they're doing it here. So if I label this one B, this one A, and this one with the Greek symbol. Oh, they labeled this one line 1, line 2. Okay, but you should recall that we have a formula that says an outside angle equals the sum of the interior angles. And we know that vertical angles are the same. So A should equal B plus that lovely little symbol. And if you solve then for this symbol, you're getting A minus B. And then they say, if you take the tangents of the triangle that you have here, you end up, and then they do a substitution. So what they're trying to give you is the same formula that you're used to seeing. No, hang on a second. Sorry, for a second I was thinking they were doing it, they were deriving it, but they're not. So it's not into the derivative formula. But if you manipulate these, you end up being able to say that the tangent of theta is m1 minus m2 over 1 plus m1 times m2. Now that looks awfully similar to this. I have something, or this one, I have something that is minusing, and then these two are multiplying. So they're saying basically, instead of writing the tangent A, tangent B, we might do the same thing with m's, because it's coming from this proof of tangents here. And they clarify, we will find that this identity is useful in calculus because it will give us the tangent of the line of intersection. So where the two are intersecting, it's telling you the tangent, if you follow that formula, the tangent of the angle of intersection of two lines. So this formula, which looks like tangent of A minus B, is also helpful when finding two lines intersecting and what the tangent of that would be. Now, example 3 says develop the identity for tangent A plus B. We don't wish to repeat that. Use it to write an equivalent expression for tangent of theta plus 45 degrees. So we're not going to recreate it every time. We're going to use it. And so we're going to have tangent of theta plus tangent of 45 over 1 minus tangent theta tangent 45. And if we simplified that, we would get 45 degrees, 1 root 2. Tangent is TOA, opposite over adjacent, so those are 1s. So basically this is tangent of theta plus 1 over 1 minus 1 times tangent theta is just tangent theta. And that's as simple as I can get that. So there is their solution to example 3. Example 4. Use the identity for tangent A plus B to developed in example 3. Okay, well, whatever. To write the identity for tangent of 2A. Okay. So now, instead of having A's and B's, they're saying have A and A. So tangent A plus tangent A is actually 2 tangent A's. And then 1 minus tangent A times tangent A would be tangent squared A. And that is on the top of page 181, another one of your identities to memorize. Like you've memorized this one, you're memorizing this one, you're memorizing the sine ones, and now this is one of the double angle ones where we did in the other lesson sine of 2A and cosine of 2A, there's tangent of 2A. Thankfully now they move from all of that to part B, where they're reminding you a lot of your area and volume formulas. So for a circle, how do you find the area of a circle? Pi times radius squared. How do you find the circumference of a circle? Pi times diameter, or 2 pi radiuses, however you prefer it. Circumference is, of course, the perimeter of. Area is how much it takes to cover the distance. If you want the area of a sector, coming from the center preferably there, you follow your formula here, but you multiply it by whatever fraction this would get. So in other words, if this were 10 degrees, you would be multiplying it by 10 out of the full 360. So like 1/36 of the full circle is how much you are wanting there. Then if you move to rectangular solids, your volume is going to be length times width times height, and your areas always end in your unit squared. Your volume would end in your unit cubed. If you have a cylinder, you're going to do area of the circular base times the height to get the volumes. That would be pi r squared times the height. And if you have the triangular solid, you're going to do the area of the triangle. So half base times the triangle's height times the height of the entire solid would be its volume. Then if you do a sphere, this one gets, your formula is a tiny touch trick here. So for the surface area of that, it's like taking the area of the circle and wrapping the circle 4 times, so it's 4 pi r squareds. The volume of it is, and I was looking to see which formula the book gave. Okay, so what I taught before in your trig class that you would have been used to seeing would be picturing encasing this sphere as a tennis ball inside its canister. And so that would be pi times the radius squared times the height of the canister. And then when we did like pyramids, we always multiplied by 1/3. So for the sphere, we memorized that it was 2/3. Now this book is giving you 4/3 pi r cubed, and that's just a manipulation of this with the height being the same as 2 radiuses. And that's how they end up manipulating that to radius cubed, and the 2 multiplying and making 4/3. I just prefer this because I'm used to doing the 1/3 with the cones as opposed to memorizing a whole nother formula with a radius cubed in it, but you do whatever works best for you. And then they move on to the cone part as a reminder, so I just kind of use that. And the perimeter of this would obviously be the pi times radius squared. Sorry. I said perimeter. I'm picturing surface area. Goodness. Surface area then would be the pi r squared for the bottom plus the piece that makes the cone. And that is a special little formula, which is pi times radius times slant height. And the slant height is this L that's the side there. And it's that lovely little cursive L. So if you do pi times the radius times this, and you may have to like make the right triangle that's here and manipulate it to find it. But the surface area is the area of the circle on the bottom. And then the cone, that special little part, pi r times slant height. Volume is going to be pi times radius squared, area of the circle, times the height of the whole thing. But again, you're picturing that as a cylinder, and so you're shaving off the part, and so we memorize that as the fraction of shaving it down by 1/3. Oh, and that's for right circular cones. They clarify if it's slanted in any way, therefore it's oblique. You can get there, you just have to use your height as like outside of the shape, but I think you'll remember when you're getting into these. All right, oh yes, on the top of 182, they finally got to their triangles, which was their half base height. They also give you that you can find the area of a triangle by doing a half base with the altitude and the sine of C. Now we did that in the trig book, but I didn't have you memorize it necessarily, but it may be helpful, especially on standardized tests that are coming up for you. If you have a trapezoid, then the formula is you're splitting it into 2 triangles, and so it's half times the height with adding of the bases together. You memorized it, you've been using it, but sometimes I think you just split it instinctively and think of it as the 2 triangles and do that, but that is the formula. And this one we barely used, and it's where you take, one of them's labeled A and one of them's labeled B, and so it's the ellipse, and so you're doing pi times the A and the B, and that's getting you the area for the ellipse. I feel like that one just came out of left field and it's new because I don't recall us doing it in trig. But now that they've reviewed all of those, example 5 says, the radius of a right circular cone is 10 centimeters. Radius is 10 centimeters. If the lateral surface area, the curved part there, of the cone is 300 pi, oh, hang on. I realized what it said. Not just the slanted thing. They're saying the area of the actual cone part. So that was the pi times radius times slant height equaled the 300 pi centimeters squared. What is the height of the cone? All right, so I can use this, killing off the pi's, and filling in that 10 is the radius to find the slant height. Yes, that will be helpful in finding the actual height, which is what they're looking for here. So that's forming a right triangle in there. So yeah, let's finish that. So the slant height would be 300 divided by 10, that's 30. centimeters. And now if this is a right triangle, the hypotenuse that I just found is the 30. So we're going to Pythagorean theorem. That's the hypotenuse, so 30 squared is 900 equals 10 squared is 100 plus the height squared. And so subtracting 800 is the height squared. The height is the square root of 800. And where do I want to do those figures? So I'm going to split that to like 8 and 100, 2 and 4, 2 and 2. 10 and 10, 2 and 5. These are impossible to read, 2 and 5. So I'm looking for sets of 2s. So I have a set here that pulled a 2 to the outside. I have a set of 2s here. That's another 2 pulling to the outside. And I have a set of 5s. That's a 5 pulling to the outside. And this 2 I never used. So 2 times 5 is 10 times 2 is 20 with the root 2 inside that I never used. So 20 root 2 centimeters were the dimensions, and that is the height. Oh, my goodness. There is another example. We are out of space there, so by all means, get some more space. Example 6. A right circular cone whose diameter is 10 and whose height is 7. Oh, these are all centimeters, 7 centimeters, is partially filled with water. Oh, that's why they drew it upside down. All right, so I paused to redraw it so I could get the water filling in there like they wanted. So it made a little more sense. So information was correct, but not with water. All right, partially filled with water. Find the volume when the depth of the water at the center is 4. So they want this to be 4 centimeters. Find the volume. Okay, so we need to do pi times the radius squared, and our I'm going to come back to the radius. Radius squared times, and then in this case, the height that we're using is the 4 for the water, and it's a cone, so it's 1/3 of that. 1/3 pi times radius squared with the 4. Yes, now let me get back to the radius. When I look at that part being a 7, and this part being a 4, then I have a right triangle. I'm trying to decide which one they want me to use. Well, there are technically 2 of them. One here with the water and one here going all the way up. And I know that when I draw this height in, I'm halving this to 5 as its radius, not its diameter. And so in this right triangle, 5 and 7, I can Pythagorean. No, I want to compare them. Yes, because this one is a 4, and I don't know what that amount would be. Okay, so let me redraw those, and that's kind of what they did. I think it will be helpful. Here's the 5, here's the 7, and that's a right triangle. Then the other one is smaller with the water. This was the 4. I don't know what this is, and yes, that's correct. And so are these similar triangles? Yes, because they have overlapping 90 degrees, and this corner is the same in both. So I can set up a proportion to find out what this value is. So 5 matches with the x, 7 matches with the 4, and my cross multiply would give me 20 divided by 7. 5 times 4 is 20 divided by 7. That's my x. So that is the radius here that I need to use, 20 over 7. Then square that. That's like 400 over 49. multiply it by a 4, divide that by a 3, somewhere in there multiply it by the 3.14 for pi. Anyway, that's all calculator work. So you should be getting 34.19 or something close to that centimeters, and volume is always cubed. That was the last example.